C1, okay, C1 to C4, you have what? 4 constants. Yes or no? Right? So we are given 4 constant. Which is C1, C2, C3, C4, right? We have 4 constant. So therefore, to find the constants, right, for boundary conditions, okay, I'm squeezing down here, my bad, okay, for boundary condition must be known. Okay, so you need to know 4 boundary condition. You don't know 4 boundary condition, you're done. Okay, you're done. Okay, so we have to know, as I said, we have to know 4 boundary condition. So we are going to apply, we're going to apply this method. Okay, we're going to look into this example. Okay, but one thing I want you to highlight to see is you have sorry, all these are a function of x. Okay, so what we have is v as a function of x, m as a function of x, theta as a function of x, y as a function of x, right? So for this case, I want you to have remember Vm theta y. Okay, I want you to remember Vm theta y, because this will help you specify your boundary condition. Okay, now let's go into an example. Okay, so let's look into example number 2. So I need to see what we want to find from example number 2. Okay, so example number 2. Okay, for example number 2, we have a gradient distributed load. Okay, we have a gradient distributed. Okay, so this is our structure, and it's simply supported. And this is our distribution. So over here is our omega naught, right? So omega naught is the height of this of the maximum height of the gradient distributed load. Okay, so over here we know now we're going to set boundary condition, right? So this is x is equal to 0. Over here x is equal to m. Okay, so we're going to set the boundary condition, and the sequence of the boundary condition I want you to follow is v m theta y, v m theta y. Okay, so boundary condition for our case is anything that we know, okay, that is equal to 0 without doing any specific calculation. So now v, when x, sorry, what am I doing? So this is x equal to L. What am I doing? Okay, I do apologize. So the distance from here to here, this is L. Okay, so v definitely not equal to 0. We don't know what it is. Okay, so don't know. M is equal to 0, right? So m, and when x is equal to 0, m is equal to 0. Why? If we were to remove the support at L, okay, rather than support L, I call this A, I call this point B. If we remove the support at point B, the entire structure will start to what? Rotate. Yes or no? That's why moment is equal to 0. Okay, I repeat again. If we at point A, right, if we remove the support at point B, the structure will rotate. That's why the moment is equal to 0. Right? So likewise, if now we're at point B, if we remove the support at point A, right, if we remove the support at point A, the whole structure will rotate. That's why moment is equal to 0. Okay. Now the slope, we have not a clue what is the slope. Why we have not a clue what is our slope? Because if I'm going to sketch the deformation pattern, the deformation pattern look like this. Right? So over here or over at point A, there is already a theta already. At point B, there's also a what? There's also a theta already. Okay, so we don't know. But one thing for sure, when x equal to 0, y is equal to x equal to L, y is equal to 0. Okay, so this is how we set the boundary condition. Now in your math course, they just give you the boundary condition without you knowing why. Okay, they just want you to see whether you can understand the mathematical approach. Now, I'm still going to focus on boundary condition. Okay, I'm still going to focus on boundary condition. Now, what if now? Okay, what if now? Okay, so this is not an example. This is just to elaborate what I'm teaching. What if now one n is a built-in now? Right? So we have the same thing. Right? We have the same thing. Right? We also have the same gradient. Right? We have the same gradient. Right? So this is still our omega naught. Right? So now, right? So this is our point A. This is our point B. Okay? That's our point A. That's our point B. Now we are going to form the boundary condition. Right? So this is x is equal to 0. X is equal to L. Okay, so this is our uniformly distributed load. So this will be our V M theta Y, V M theta Y. Okay. So when x is equal to 0, V, we have not a clue. We don't know what is it. At x is equal to L, we know that V is equal to what? 0. Why V is equal to 0? Because point B, right? Point B is allowed to move. Okay. Then when x is equal to 0, the moment now, right, is going to be what? The maximum. It will not be equal to 0, right? Because if you point B has no support, the beam is not rotating, right? Now when x is equal to L, when you remove point A, right? If point A is removed, the beam will what? Want to rotate, so the moment is equal to 0. Okay. So if I'm going to sketch how this thing will deform, right? This thing will deform this way, right? So if you were to convince yourself, why is it going to deform this way? At point A, you just take a ruler. At point A, you hold your finger. At point B, you push a load down, right? You use the other hand to push a load down. You can see at point A, you have no slope at all. Okay, so point A, the slope is equal to 0, or x equal to 0 equal to 0, right? And then y over here is equal to 0. Y at x equal to L, we don't know. So you see the boundary condition already changes. So when the boundary condition changes, the constant change, yes or no, right? So I'm going to highlight one more example before I let you go for a break. Now, what if now, okay, same thing. That is the power of this technique, okay? Now the same thing, right? Also a cantilever beam, right? also a cantilever beam. Now, at point B, so I'm going to wipe all this out. Yeah, so at point B now, I'm going to have a support. And this is our L, right? So now our boundary condition is we don't know what is this. We don't know what is this, right? The moment we know it's going to be maximum, but it's not really a boundary condition, is it? But we know down here moment is equal to 0. Theta is equal to 0. Over here, we have not a clue. The slope is not equal to 0 because when the structure deform, it's going to deforming this way. Okay, it's going to deform this way. Right? So it's not equal to 0. Right? However, y is equal to what? 0. Okay. So you can see physically what all these boundary condition actually means now. Yes or no? Right? You can physically see, hey, now I understand what all these condition actually mean now. Right? So you can see all these boundary condition. If you have a math problem, they say solve this problem with this boundary condition and a different boundary condition. Now you can physically see for yourself what each boundary condition actually mean physically in structure analysis. Okay, so that is the strength of this method. Its strength is also its weakness. You have to know the boundary condition. If you don't know boundary condition, you cannot use this method at all. Okay, so go for a break. We come back at 8:45. We will carry on. Okay, thank you.